Hey, welcome to the Night Scientist of Discovery. I'm so happy you're here with me today. There's something truly magical about those quiet moments when we can sit back, relax, and let our minds wander to the most extraordinary places our planet has ever been. Whether you're settling in for the evening, taking a break from your day, or simply looking for a gentle escape into the wonders of our world, you've found the perfect place to unwind and explore together. I want you to get comfortable, maybe grab a warm cup of tea or coffee, and let yourself sink into this story that's been millions of years in the making. We're going to take our time, breathe deeply, and discover something absolutely incredible about our Earth's past. There's no rush here, no pressure to keep up with anything fast-paced or overwhelming. This is your moment to slow down and marvel at the incredible journey our planet has taken, long before any of us were here to witness it. Today we're diving into the fascinating world of when Earth first froze solid, a time so extraordinary and so completely different from anything we know today that it almost feels like science fiction. But this isn't a story from imagination. This is the real, incredible history of our own planet. Picture this: our entire Earth, from the tallest mountains to the deepest ocean floors, covered in a blanket of ice so thick and so complete that our planet looked like a giant, glittering snowball floating through space. It's a story that will take us back hundreds of millions of years, to a time when the rules of climate and weather were so different that our world became something almost unrecognizable. Imagine waking up one morning and looking out your window to find that everything, absolutely everything, has been covered in snow and ice. Not just your yard, not just your city, but literally every single place on Earth. The oceans frozen solid, the continents buried under miles of ice, even the tropical regions where we think of warm beaches and swaying palm trees, all of it transformed into a frozen wasteland that stretches from one horizon to the next. This might sound like the plot of a disaster movie, but this extraordinary scenario actually happened to our planet, not once, but possibly several times during a period that scientists have come to call Snowball Earth. And when I say it happened, I mean it really truly happened. Our beautiful blue and green planet, the one we know and love today with its diverse climates and ecosystems, became a pale, white sphere of ice that reflected almost all of the sun's light back into space. Let's take a moment to really let that sink in. Every beach you've ever walked on, every forest you've ever hiked through, every lake you've ever swum in, all of it would have been buried under layers of ice so thick that if you could somehow travel back in time to see it, you might not even recognize our planet. The ice wasn't just a thin coating like the frost you might scrape off your car windshield on a cold morning. We're talking about ice sheets that were hundreds, sometimes thousands of feet thick, stretching across continents like massive frozen blankets. Now, you might be wondering how we could possibly know about something that happened so long ago. And that's a wonderful question. After all, there weren't any people around to write down what they saw, no cameras to capture the frozen landscapes, no weather stations recording temperatures. The story of Snowball Earth is written in the rocks themselves, in tiny details that scientists have spent decades learning to read like pages in the most incredible book ever written. Think of it like being a detective, but instead of solving a mystery that happened last week or last year, you're solving a mystery that happened between 750 and 580 million years ago. The clues are subtle, hidden in layers of rock that formed when the ice finally melted, preserved in the chemical signatures of ancient oceans, and embedded in the very structure of mountain ranges that rose and fell during these frozen times. One of the most fascinating clues comes from something called drop stones. Picture this. During the Snowball Earth periods, massive icebergs would break off from the enormous ice sheets and float out into what little liquid water remained in the deepest parts of the oceans. These icebergs carried with them rocks and boulders that had been frozen into the ice, sometimes stones that were quite large and heavy. As the icebergs slowly melted and drifted across the ancient seas, these rocks would eventually drop to the ocean floor, landing in soft mud and sediment that would later turn to stone. Today, when geologists find these drop stones in rock formations that clearly formed in tropical regions, they know they're looking at evidence of something extraordinary. It's like finding a snowball in the desert, a sign that conditions were once so different that ice existed in places where it seems impossible. These drop stones tell us that even near the equator, where our planet receives the most direct sunlight, and where today we find our warmest climates, there was once enough ice to form glaciers and icebergs. Another clue comes from something called banded iron formations, which sound technical but tell us an incredible story about what was happening in the oceans during these frozen times. When Earth's surface was covered in ice, very little oxygen could get into the ocean water from the atmosphere. Without oxygen, iron in the ocean water behaved very differently than it does today, creating distinctive patterns in the rocks that formed during those times. It's like finding fingerprints at a crime scene, except these fingerprints tell us about the chemistry of ancient oceans and how different they were from the seas we know today. To understand how our planet could have possibly become such a frozen wasteland, we need to travel back in time and imagine Earth as it was before the Great Freezing began. This was a world that would seem alien to us in many ways, yet it was the same planet we call home today. The continents were arranged very differently, clustered together in ways that would dramatically affect how heat moved around the planet. Picture the Earth's continents not spread out across the globe as they are today, but gathered together in a massive supercontinent that scientists call Rodinia. This enormous landmass, whose name means motherland in Russian, was like nothing we see on Earth today. Imagine all of our current continents, North America, South America, Africa, Europe, Asia, Australia and Antarctica, all pressed together into one gigantic piece of land surrounded by a single vast ocean. This arrangement of continents had profound effects on how our planet's climate system worked. Today, we have ocean currents that carry warm water from the tropics toward the poles and bring cooler water back toward the equator. These currents act like a giant heating and cooling system for our planet, helping to moderate temperatures and prevent any one region from becoming too hot or too cold. But when most of the land was concentrated in one supercontinent, these ocean currents couldn't flow in the same patterns. The positioning of Rodinia was particularly important because much of this supercontinent was located in tropical and subtropical regions, right where our planet receives the most intense sunlight. You might think this would make the Earth warmer, but it actually set up conditions for the opposite to happen. When continents are positioned in the tropics, they undergo intense weathering processes that can actually remove carbon dioxide from the atmosphere. Let me explain how this works in a way that's easy to picture. When rocks are exposed to warm, humid tropical conditions, they break down through chemical weathering. Rainwater, which is naturally slightly acidic, reacts with minerals in the rocks and slowly dissolves them. This process doesn't just break rocks into smaller pieces, it actually consumes carbon dioxide from the atmosphere. The carbon dioxide dissolves into the rainwater, making it even more acidic, and then gets carried away by rivers and streams, eventually ending up in the ocean where it can become incorporated into marine organisms and ocean sediments. Now, carbon dioxide is what we call a greenhouse gas, which means it helps trap heat in our atmosphere. The more carbon dioxide there is in the air, the warmer our planet tends to be. But during the time leading up to Snowball Earth, the intense tropical weathering of the Rodinia supercontinent was pulling massive amounts of carbon dioxide out of the atmosphere. It was like someone slowly turning down the thermostat for the entire planet. As carbon dioxide levels dropped, Earth began to cool. At first, this cooling might have been gradual and not particularly dramatic. The polar regions, which are always the coldest parts of our planet, began to accumulate more ice and snow during their winter seasons, and less of it melted away during the summers. This might not sound like a big deal, but it triggered what scientists call a positive feedback loop, though in this case, the results were anything but positive for most life on Earth. Here's how this feedback loop worked, and it's both elegant and terrifying in its simplicity. As more ice and snow accumulated at the poles, more of the sun's energy was reflected back into space instead of being absorbed by the Earth's surface. Ice and snow are incredibly reflective, much more so than bare ground, vegetation or ocean water. When sunlight hits ice, most of it bounces right back into space, like light reflecting off a mirror. This increased reflection, which scientists call albedo, meant that even less of the sun's energy was staying on Earth to warm the planet. As Earth cooled further, the ice sheets began to expand, covering more and more of the planet's surface. And as they expanded, they reflected even more sunlight back into space, causing even more cooling. It was like a runaway process that fed on itself, each step making the next step not only possible but inevitable. The cooling didn't stop at the poles. As global temperatures dropped, ice began forming at higher and higher latitudes, creeping ever closer to the equator. The process would have taken thousands or tens of thousands of years, but from a geological perspective, it was remarkably fast. Imagine the ice sheets as slow-moving but unstoppable forces, advancing year after year, decade after decade, covering forests and grasslands, freezing rivers and lakes, and eventually reaching the sea. When the ice reached the oceans, something even more dramatic happened. The surface of the sea began to freeze, starting near the shores where the ice sheets met the water, then gradually extending further and further out to sea. Unlike the ice sheets on land, which could be hundreds or thousands of feet thick, the sea ice was relatively thin at first, maybe just a few feet deep. But even thin ice is incredibly effective at reflecting sunlight, and as more and more of the ocean surface froze over, the albedo effect became even stronger. There comes a moment in the story of Snowball Earth that feels almost mythical in its significance, a turning point where our planet crossed a threshold from which there seemed to be no return. Scientists believe this critical moment occurred when ice coverage reached approximately 30 degrees latitude, both north and south of the equator. To put this in perspective, 30 degrees north runs through places like New Orleans, Cairo, and northern India, while 30 degrees south passes through places like Johannesburg, Santiago, and Brisbane. Imagine standing at one of these locations today, perhaps on a warm beach in Florida, or in the bustling streets of a Middle Eastern city, and trying to picture the landscape completely transformed by advancing walls of ice. It seems impossible, doesn't it? These are regions where people today never see snow, where palm trees grow and where the sun feels warm on your skin almost year-round. Yet during the Snowball Earth events, even these relatively tropical locations were overtaken by the relentless advance of the ice. Once the ice reached this critical latitude, the albedo feedback loop became so powerful that it essentially took on a life of its own. The amount of solar energy being reflected back into space was now so enormous that the planet's energy balance had fundamentally shifted. Earth was losing more heat to space than it was receiving from the sun, and this energy deficit drove the ice to advance even further toward the equator. The mathematics of this process are both beautiful and terrifying. As the ice coverage increased, the planet's overall reflectivity increased in what scientists describe as an exponential fashion. This means that each additional degree of latitude covered by ice had an even greater cooling effect than the degree before it. It was like a ball rolling down a hill that keeps getting steeper, gathering speed and momentum until it becomes impossible to stop. What makes this story even more remarkable is that once the ice reached the equatorial regions, our planet would have been caught in what appeared to be a stable, frozen state. The ice sheets that covered the continents weren't just sitting on the surface, they were actively flowing and moving, like slow-motion rivers of ice that carved and shaped the landscape beneath them. These continental ice sheets could have been several miles thick in some places, representing an almost unimaginable amount of frozen water. The frozen oceans presented their own unique characteristics. While the sea ice wasn't as thick as the continental glaciers, it would have been substantial enough to support its own ecosystem of sorts. The ice would have been constantly shifting and moving, cracking and reforming, creating pressure ridges and leads of open water that would quickly refreeze. The sounds of this frozen ocean would have been extraordinary. The deep groaning and cracking of ice under pressure, the sharp reports of ice breaking, and the subtle whisper of wind across the frozen surface. But perhaps the most remarkable aspect of this frozen world was its incredible brightness. Imagine looking at Earth from space during a Snowball Earth event. Instead of the familiar blue marble with swirling white clouds and brown and green continents, you would see something that looked more like a giant pearl or opal, gleaming brilliantly as it reflected the sun's light. The planet would have been almost blindingly bright, reflecting somewhere between 60 and 90% of the sunlight that hit it, compared to the roughly 30% that Earth reflects today. This extraordinary reflectivity created a situation where the sun, despite shining just as brightly as it does today, could not provide enough energy to melt the ice. It was as if Earth had wrapped itself in a mirror-like blanket that deflected the very energy source that could have freed it from its frozen state. The planet had essentially created its own prison of ice, and the key to escape seemed to have been thrown away. The atmospheric conditions during this time would have been unlike anything we can easily imagine. With most of the planet's water locked up in ice, the atmosphere would have been incredibly dry. There would have been very little water vapour to form clouds, which meant that the skies would have been clearer than anything we see today. Without clouds to trap heat at night or block sunlight during the day, the temperature variations would have been extreme, though always remaining well below freezing. the winds during Snowball Earth would have been both constant and fierce. With such extreme temperature differences between the relatively warmer equatorial ice and the incredibly cold polar regions, massive pressure systems would have developed, driving winds across the frozen landscape at speeds that would have been dangerous to any life form that might have somehow survived on the surface. These winds would have carved the ice into fantastic shapes, creating features that might have resembled the otherworldly landscapes we see today in Antarctica, but on a scale covering the entire planet. It's important to pause here and really consider the magnitude of what we're describing. This wasn't just a particularly harsh winter, or even an ice age like the ones that occurred much more recently in Earth's history. Those ice ages, dramatic as they were, still left vast regions of the planet unfrozen. During the most recent ice age, which ended only about 11,000 years ago, places like Florida, Mexico, and most of Africa remained warm and ice-free. But Snowball Earth was something altogether different, a complete transformation of our planet's surface into a world that would have been nearly unrecognizable. Now, you might be wondering about life during these extraordinary frozen periods, and that's one of the most fascinating parts of this entire story. When scientists first proposed the Snowball Earth hypothesis, one of the biggest questions was how life could possibly have survived such extreme conditions. After all, this was a time when complex life was just beginning to evolve, when the most sophisticated organisms on Earth were still microscopic, and when the foundations for all future evolution were being laid down. The answer to this puzzle takes us to some of the most remote and extreme places on our planet today, places that might give us clues about how life persisted during those frozen eons. Think about the deep ocean vents that exist on the seafloor today, where superheated water rich in minerals shoots up from cracks in the Earth's crust. These underwater oases support entire ecosystems without any energy from the sun, relying instead on chemical processes that turn minerals into food. During Snowball Earth, similar hydrothermal vents would have continued operating beneath the frozen ocean surface. The ice might have been hundreds of feet thick, but beneath it, the ocean would have remained liquid, kept warm by the heat rising from the Earth's interior. These underwater refuges would have been like hidden sanctuaries, warm pockets of life in an otherwise frozen world. The organisms living around these vents wouldn't have needed sunlight to survive. They could extract energy directly from the chemicals dissolved in the hot water. But the deep-sea vents weren't the only places where life might have found a way to persist. Scientists have discovered that even in the thickest ice sheets, there can be thin films of liquid water that exist between ice crystals, or small pockets of unfrozen water that remain liquid due to the pressure of the ice above or the presence of dissolved salts and other compounds that lower the freezing point.
These microscopic environments within the ice itself could have served as tiny refuges for bacterial life. We know this is possible because we found similar communities of organisms living in glacier ice today. In places like Antarctica and Greenland, these ice-dwelling bacteria are incredibly hardy, capable of surviving in conditions that would quickly kill most other forms of life. They've developed special proteins that prevent ice crystals from forming inside their cells. And they can remain dormant for incredibly long periods, waiting for conditions to improve. The organisms that survived Snowball Earth would have been primarily prokaryotes, bacteria and archaea that were already adapted to extreme conditions. Some of these might have been photosynthetic, capable of using sunlight to produce energy, while others would have been chemosynthetic, deriving energy from chemical reactions. The photosynthetic organisms would have faced particular challenges during Snowball Earth, since the thick ice would have blocked most sunlight from reaching the ocean water beneath. However, recent research has suggested that even thick sea ice isn't completely opaque to light. A small amount of sunlight can penetrate through several feet of ice, and this might have been enough to sustain some photosynthetic life, particularly if these organisms had evolved to be extremely efficient at capturing and using whatever light was available. It's a bit like how some plants today can survive in the deep shade of forest floors, making the most of the tiny amount of sunlight that filters down through the canopy. The survival of life during Snowball Earth also depended on the fact that the frozen conditions were absolutely uniform across the entire planet. even during the most severe frozen periods, there would have been variations in ice thickness, cracks and leads in the sea ice, and possibly even small areas of open water where geological activity or ocean currents prevented complete freezing. These variations would have created a patchwork of microenvironments, each with slightly different conditions and possibilities. For life, one of the most intriguing possibilities is that life might have survived in liquid water beneath the ice sheets on land today. Scientists have discovered extensive networks of liquid water beneath the ice sheets of Antarctica, kept liquid by geothermal heat from below and the insulating effect of the thick ice above during Snowball Earth. Similar subglacial lakes and streams could have existed, providing refuge for organisms that had been living in freshwater environments before the Great Freezing began. The chemical composition of these hidden water bodies would have been quite different from normal lakes and rivers, cut off from the atmosphere and from the normal cycling of nutrients that occurs in surface waters. These subglacial environments would have developed their own unique chemistry. Minerals dissolved from the rocks beneath the ice would have accumulated in the water, creating conditions that might have actually been favorable for certain types of extremophile bacteria. Perhaps most remarkably, some scientists have suggested that the Snowball Earth events might not have been an obstacle to evolution, but rather a catalyst for it. The extreme conditions would have created intense selective pressure, favoring organisms that could adapt to cold, low light, and chemically unusual environments. This evolutionary pressure might have driven the development of new biochemical pathways, new forms of metabolism, and new strategies for survival that would later prove crucial when the ice finally melted and life could expand once again. Isolation of different populations of organisms in separate refuges during Snowball Earth could also have promoted speciation, the process by which new species evolve when populations of the same organism are separated for long periods and exposed to different environmental pressures. They can diverge genetically and eventually become distinct species. The millions of years during which Earth remained frozen would have provided ample time for this kind of evolutionary divergence to occur. When we think about the incredible resilience of life during these frozen periods, it's worth remembering that the organisms that survived Snowball Earth were the ancestors of all life that exists today, including us. Every plant, animal, fungus, and microorganism on Earth today carries in its DNA the legacy of ancestors that somehow managed to persist through conditions more extreme than anything our planet has experienced since. In a very real sense, we are all descendants of Snowball Earth survivors, inheritors of evolutionary innovations that were forged in the crucible of a frozen world. The story of how life persisted during Snowball Earth becomes even more fascinating when we consider the extraordinary chemical changes that were taking place in the oceans beneath all that ice. These weren't just frozen seas, sitting motionless for millions of years. They were dynamic, chemically active environments where some of the most important processes in Earth's history were quietly unfolding in the darkness below the ice. When the ocean surface froze over, it created what scientists describe as a closed system, cutting off the normal exchange of gases between the ocean and the atmosphere. In today's oceans, this exchange is crucial for maintaining the chemical balance that supports marine life. Oxygen from the atmosphere dissolves into seawater, while carbon dioxide moves back and forth between the air and sea depending on temperature, pressure, and biological activity. But during Snowball Earth, this vital exchange was largely blocked by the ice barrier. The consequences of this isolation were profound and far-reaching. Without fresh oxygen entering from the atmosphere, The dissolved oxygen in the seawater was gradually consumed by bacteria and other organisms through respiration and decay processes. As oxygen levels dropped, the ocean chemistry shifted in ways that hadn't been seen for billions of years, returning to conditions more like those that existed in Earth's earliest history. In these oxygen-poor waters, iron behaved very differently than it does in modern oceans. Today, iron in seawater quickly oxidizes and precipitates out, forming rust-colored sediments on the ocean floor. But in the low-oxygen waters beneath the Snowball Earth ice, iron remained dissolved in the water column, creating the conditions for the formation of those distinctive banded iron formations that provide us with evidence of these ancient frozen periods. These chemical changes weren't just academic curiosities. They had real implications for the organisms trying to survive in these harsh conditions. Many bacteria had to switch to entirely different forms of metabolism, using chemical processes that didn't require oxygen. Some began using sulfur compounds instead of oxygen for their cellular respiration, producing hydrogen sulfide as a waste product. Others turned to various forms of fermentation, breaking down organic compounds in ways that released energy without consuming oxygen. The accumulation of these alternative metabolic processes created a complex chemical ecosystem beneath the ice. Hydrogen sulfide, methane, and other gases produced by bacterial metabolism began to accumulate in the water, creating an environment that would have been toxic to most modern marine organisms but was perfectly suited to the hardy microbes that had evolved to survive in extreme conditions. One of the most remarkable aspects of this underwater chemistry was the role of dissolved carbon dioxide. As we mentioned earlier, the weathering of rocks on the frozen continents was pulling carbon dioxide out of the atmosphere. But this carbon dioxide didn't just disappear. Much of it eventually made its way to the oceans through rivers and groundwater, where it dissolved into the seawater and began to accumulate beneath the ice. This dissolved carbon dioxide made the ocean water increasingly acidic over time, creating conditions that were challenging for any organisms that built shells or skeletons from calcium carbonate. However, the increasing acidity also made certain minerals more soluble, releasing nutrients like phosphorus and nitrogen that could support bacterial growth. It was a delicate balance between harsh conditions that made survival difficult and chemical changes that provided new opportunities for adapted organisms. Circulation patterns in these ice-covered oceans would have been unlike anything we see today, without wind-driven surface currents and with limited temperature differences between surface and deep water. The normal patterns of ocean circulation would have been greatly reduced, however. There would still have been some movement driven by differences in salinity, density, and the heat rising from hydrothermal vents on the ocean floor. These sluggish circulation patterns meant that nutrients and gases could accumulate in certain regions while being depleted in others, creating a patchwork of different chemical environments within the same ocean. Some areas might have been relatively rich in nutrients and supportive of bacterial communities, while others might have been nearly sterile. This chemical heterogeneity would have created numerous ecological niches, each with its own possibilities and challenges for survival. Perhaps most intriguingly, some scientists have proposed that the unique chemical conditions beneath Snowball Earth ice might have facilitated entirely new forms of biochemistry. The high concentrations of dissolved minerals, the absence of oxygen, and the stable, cold temperatures could have allowed for chemical reactions and metabolic pathways that simply aren't possible under normal Earth conditions. Some of these biochemical innovations might have persisted even after the ice melted, contributing to the remarkable diversity of microbial metabolism that we see in extreme environments today. The role of volcanic activity during Snowball Earth adds another layer to this chemical story. Volcanic eruptions continued throughout the frozen periods, adding heat, gases, and minerals to the system. Underwater volcanic activity would have created local hotspots where temperatures were higher and chemical activity was more intense. These volcanic inputs would have been particularly important for maintaining the chemical cycling that kept some parts of the ocean habitable for microbial life. As we consider the incredible complexity of these chemical processes, it's worth reflecting on how they set the stage for everything that came after, the organisms that survived. Snowball Earth didn't just endure these harsh conditions. They adapted to them, evolved new capabilities, and developed biochemical tools that would prove invaluable when Earth finally began to warm again. Chemical innovations forged in the depths of the frozen oceans became part of the genetic heritage that all subsequent life would inherit and build upon as our planet spins through the cosmic dance of time. We find ourselves drawn deeper into one of Earth's most extraordinary chapters. Picture, if you will, a world where the very concept of seasons becomes meaningless, where the gentle warmth of sunlight struggles against an ever-growing blanket of white that stretches from pole to pole. This is the story of how our vibrant, blue-green world transformed into something that would be nearly unrecognizable to us today. Gleaming sphere of ice suspended in the darkness of space. The journey toward this frozen state didn't happen overnight, like flipping a switch in a cosmic room. Instead, it was a gradual process, as gentle and inexorable as the changing of seasons, but stretched across millions of years. Imagine the Earth as a massive, complex machine with countless moving parts, each one influencing the others in ways both subtle and profound. The atmosphere breathes in and out, cycling gases like oxygen and carbon dioxide in a delicate balance. The oceans flow in great currents, carrying heat from the equator toward the poles like a planetary circulatory system. The continents drift slowly across the surface, changing the very geography of our world and altering the paths these currents can take during the time we're exploring. Roughly 750 to 580 million years ago, something remarkable was happening to this intricate system. The continents, those massive puzzle pieces of rock and soil, were arranged very differently than they are today. Most of them were clustered near the equator, creating a configuration that scientists sometimes call a supercontinent. This wasn't quite like the supercontinent Pangaea that would form much later, but rather a collection of landmasses that fundamentally changed how heat moved around our planet. Think of the oceans as Earth's heating system, carrying warm water from tropical regions toward the colder poles, much like the radiators in an old house distribute warmth from a central furnace. When continents are positioned near the equator, they act like barriers, disrupting these crucial currents. It's similar to placing furniture in front of your home's heating vents. The warm air can't circulate properly, and some rooms become colder than others. In Earth's case, this disruption meant that less heat was being transported to the polar regions, allowing ice to begin forming and persisting year after year. But the story of Earth's great freezing involves more than just the position of continents. The atmosphere itself was undergoing dramatic changes, and one of the most significant factors was the amount of carbon dioxide in the air. Carbon dioxide, that invisible gas we exhale with every breath, acts like a blanket around our planet, trapping heat that would otherwise escape back into space. It's what scientists call a greenhouse gas, and its presence in our atmosphere is crucial for maintaining temperatures that can support life as we know. During the lead-up to the Snowball Earth events, something was systematically removing carbon dioxide from the atmosphere. This process, called weathering, is one of nature's most patient and persistent workers. Picture rainwater falling from the sky. It's not pure water, but rather a weak acid. Having absorbed carbon dioxide from the air during its journey downward, when this slightly acidic rain hits rocks, particularly certain types of volcanic rocks, it begins a slow chemical reaction that literally pulls carbon dioxide out of the atmosphere and locks it away in new minerals. This weathering process happens all the time, everywhere on Earth, but its effects are usually balanced by other processes that release carbon dioxide back into the air. Volcanoes, for instance, are constantly breathing out this crucial gas, helping to maintain the atmospheric balance that keeps our planet warm. However, during the period leading up to the Great Freeze, this balance was disrupted. The continents were positioned in tropical regions, where weathering happens most rapidly due to the warm, humid conditions. Meanwhile, volcanic activity may have been at a relative low point, reducing the amount of carbon dioxide being returned to the atmosphere as the concentration of carbon dioxide in the atmosphere slowly declined. Earth's natural greenhouse effect weakened. It was like gradually removing blankets from a sleeping person on a cold night at first. The change might be imperceptible, but eventually, the cold begins to seep in. The planet's average temperature started to drop, and ice began to form at higher latitudes and elevations where it had never persisted before. This is where the story takes on an almost magical quality. Though the magic is really the incredible physics of ice and light. Ice, you see, is one of nature's most perfect mirrors. When sunlight hits a dark surface like soil or rock, most of that energy is absorbed and converted to heat, warming the surface and the air above it. But when sunlight hits ice or snow, something very different happens. Instead of absorbing the energy, the white surface reflects most of it back toward space, like a cosmic mirror sending the sun's gift away unused. Scientists call this the albedo effect, and it becomes a powerful feedback loop once it gets started. As more ice forms, more sunlight is reflected away, which leads to further cooling, which allows even more ice to form. It's like a snowball rolling down a hill, gathering more snow and momentum as it goes. Except in this case, the snowball was our entire planet, and the hill was a descent into an ice age unlike any other in Earth's history. The expansion of ice coverage didn't happen uniformly across the globe. Instead, it began in the places where ice naturally forms first, the higher latitudes near the poles and the elevated regions of continents. These areas became brilliant white patches on our planet's surface, reflecting away the sun's energy and creating local cooling effects that gradually spread outward like ripples in a pond. As the ice sheets grew larger and thicker, they began to influence weather patterns in profound ways. The presence of massive ice sheets changes how air moves around the planet, creating new wind patterns and altering the paths of storms. Cold air flows off the ice like water flowing downhill, creating bitter winds that can freeze rivers and lakes that had never frozen before. The growing ice sheets also began to lock up tremendous amounts of water, causing sea levels to drop and exposing new areas of land to the harsh cold conditions. In the gentle rhythm of Earth's ancient story, there comes a moment, not a single instant, but rather a slow realization spreading across millennia, when the planet crosses an invisible threshold. This is the tipping point. That critical moment when the processes driving the cooling become so powerful that they overwhelm any natural tendency toward warming. It's like watching a careful balance slowly tip until gravity takes over. and what was once stable becomes inevitable motion toward a new state. Picture our planet during this crucial time, perhaps 720 million years ago, as a world caught between two destinies. In some regions, life continued much as it had for millions of years. Simple organisms floated in warm seas, building the first coral-like structures and creating the layered rock formations we call stromatolites. The water was still liquid in many places, still capable of supporting the delicate chemistry that makes life possible. But elsewhere, advancing walls of ice crept steadily toward the equator, carrying with them a silence that few places on Earth had ever known. Tipping point wasn't marked by any dramatic event that ancient observers might have noticed. There were no massive volcanic eruptions, no asteroid impacts, no sudden catastrophes. Instead, it was the accumulation of countless small changes, like water drops slowly filling a basin until it finally overflows. Each year brought slightly more ice coverage than the year before. Each decade saw the white patches on the planet's surface grow a little larger. Each century witnessed the slow retreat of open water and the advance of frozen landscapes. What made this tipping point so significant was the way different systems on Earth began to reinforce each other's effects. The albedo feedback loop we discussed earlier was just one piece of a much larger puzzle. As ice coverage expanded, it didn't just reflect more sunlight. It also began to change the very composition of the atmosphere in ways that accelerated the cooling process. When ocean water freezes, it doesn't just lock away liquid water. It also traps tiny bubbles of air within the ice. These bubbles contain samples of the ancient atmosphere, like time capsules that scientists can study today to understand what the air was like millions of years ago. But more importantly for our story, the formation of ice also affects how gases move between the ocean and the atmosphere. Normally, the oceans and atmosphere are in constant communication, exchanging gases like carbon dioxide in a delicate dance of equilibrium. Warm water can hold less dissolved gas than cold water, so as oceans warm, they tend to release carbon dioxide into the atmosphere. Conversely, as they cool, they absorb more of this crucial greenhouse gas from the air. But when the ocean surface begins to freeze, this exchange becomes much more limited. The ice acts like a lid on a pot, preventing the normal flow of gases between water and air. This creates another feedback loop that accelerates the cooling process. As more ocean surface freezes, less carbon dioxide can be exchanged between the ocean and atmosphere. But here's where the story becomes particularly interesting. The weathering process on land continues to remove carbon dioxide from the atmosphere, even as the ocean's ability to release it back becomes more and more limited. It's like having a drain that continues to empty a bathtub while the faucet is slowly being turned off. The result was a steady, relentless decline in atmospheric carbon dioxide levels, which weakened Earth's greenhouse effect even further. As the planet's natural blanket became thinner and thinner, temperatures dropped more rapidly, allowing ice to advance into regions where it had never been stable before. The tropics, those warm bands around Earth's middle that we think of as permanently warm and humid, began to feel the bite of winter. For the first time in hundreds of millions of years, the advancing ice brought with it more than just cold temperatures. It transformed entire landscapes, grinding down mountains and carving new valleys as the massive ice sheets moved across the continents. The weight of all this ice was almost incomprehensible. Imagine a layer of frozen water several kilometers thick covering entire continents. This enormous mass actually pressed down on the Earth's crust, causing the land itself to sink under the burden. Like pressing down on a soft cushion with your hand. The ice sheets weren't static, frozen monuments. They were dynamic, living systems in constant motion, flowing like extremely slow rivers from areas where snow accumulated toward areas where it could find release. The movement was imperceptible on human timescales, perhaps only a few meters per year, but over thousands and millions of years. These glacial rivers carved entirely new features into the landscape. They scraped away soil and loose rock, polished solid stone to a mirror-like smoothness, and carried enormous boulders hundreds of kilometers from their original homes. As the ice sheets grew larger and more numerous, they began to merge with one another, forming continuous walls of frozen water that stretched across entire continents. The ice that had once been confined to mountain peaks and polar regions now flowed down into valleys, across plains, and eventually reached the edges of the still unfrozen oceans. When these terrestrial ice sheets met the sea, they created massive walls of ice that extended far out into the water, floating on the surface like frozen harbors that stretched to the horizon. The oceans themselves were undergoing their own transformation during this period. As more and more water became locked up in ice sheets on land, sea levels dropped dramatically. Coastlines that had been underwater for millions of years suddenly found themselves exposed to the cold air and bitter winds flowing off the ice. These newly exposed lands quickly froze as well, creating even more reflective surface area that accelerated the cooling process. Meanwhile, the remaining liquid oceans became increasingly isolated from one another as ice barriers formed between them. Ocean currents that had circulated for millions of years, carrying warm water from the equator toward the poles, found their paths blocked by walls of ice. Without these currents to distribute heat around the planet, the temperature differences between different regions became more extreme, and the overall cooling process accelerated even further. And so we arrive at one of the most extraordinary chapters in our planet's long story, a time when Earth transformed into something that would seem alien to us today. Picture, if you can, looking down at our world from space during the height of a Snowball Earth event. Instead of the familiar blue and green marble we know and love, you would see a gleaming white sphere, brilliant and pristine, reflecting the sun's light. Like a cosmic pearl suspended in the darkness of space. This wasn't simply a more severe version of the ice ages that would come much later in Earth's history. Those later ice ages, dramatic as they were, left large portions of the planet ice-free, with liquid oceans and temperate regions where life could continue much as it always had. The Snowball Earth events were different. They were global in scale, covering even the tropical regions with ice and snow, creating conditions that were unlike anything our planet had experienced before or would experience again. Imagine standing on the surface of this frozen world. Though, of course, no human observers existed to witness this incredible transformation. The landscape would have stretched out in all directions as an endless expanse of white, broken only by the dark peaks of the tallest mountains poking through the ice like islands in a frozen sea. The silence would have been profound, not the profound quiet of a snowy winter day, but the deep, almost spiritual silence of a world where most forms of movement in life had been temporarily suspended. The ice itself wasn't uniform across the planet's surface, near the equator, where some liquid water might still have existed in the deepest parts of the oceans. The ice would have been relatively thin, perhaps only a few meters thick in some places, but toward the poles and in the mountainous regions, the ice accumulated to incredible depths, forming layers upon layers that chronicled thousands of years of snowfall and freezing. Some of these ice sheets may have been several kilometers thick, rivaling the massive ice caps we see in Antarctica today, but covering areas many times larger. Formation of such thick ice sheets created fascinating and complex structures within the frozen water itself as new snow fell year after year. It compressed the older layers beneath, gradually transforming fluffy snowflakes into dense, crystalline ice. This process created distinct layers within the ice sheets, much like the rings in a tree trunk, each one recording the conditions during a particular period of time. Some layers might be clear and pure, formed during periods of steady, gentle snowfall. Others might contain bubbles of ancient air, trapped dust particles, or even tiny fragments of rock carried by the wind. The weight of all this accumulated ice created incredible pressures at the bottom of the ice sheets. Under such pressure, ice behaves almost like a very thick liquid, flowing and deforming in response to the enormous forces acting upon it. This allowed the ice sheets to spread outward from the areas where snow accumulated most heavily, slowly engulfing new territories in their frozen embrace. The movement was so slow as to be imperceptible, but over thousands of years, these glacial flows could travel vast distances, carrying with them fragments of the landscapes they had covered. Where the ice sheets reached the edges of continents, they encountered the ocean and created some of the most spectacular features of the Snowball Earth world. These meeting points between land ice and sea would have been dramatic landscapes of towering ice cliffs, some rising hundreds of meters above the frozen ocean surface. As the ice sheets continued to flow seaward, enormous chunks would occasionally break off and crash into the water below, creating icebergs of unprecedented size that drifted across the frozen seas like floating mountains. But even in this seemingly lifeless world, Earth's dynamic systems continued to operate, though in ways very different from what we see today. Planet's interior remained hot, heated by the decay of radioactive elements and the residual warmth from Earth's formation billions of years earlier. This internal heat found ways to reach the surface, creating pockets of relative warmth even in the midst of the global freeze. Volcanic activity continued during the Snowball Earth periods, though it took on a very different character than volcanic eruptions in warmer times, when lava emerged from the Earth's interior onto a surface covered by thick ice. The results were dramatic and spectacular. The incredible heat of the molten rock instantly vaporized any ice it contacted, creating enormous clouds of steam that rose high into the cold atmosphere. These volcanic regions became islands of activity in an otherwise static world, surrounded by landscapes of melted and refrozen ice that created unique and complex terrains. The interaction between volcanic heat and the ice sheets also created fascinating microenvironments that may have served as refuges for life during these harsh periods. Around volcanic vents and hot springs, small areas of liquid water could persist, even when the rest of the planet was frozen solid. These oases of warmth would have been like tiny tropical islands in an Arctic world, maintaining temperatures and conditions that could support the simple forms of life that existed during this period. Geothermal heat also created complex systems beneath the ice sheets themselves, just as we find liquid water beneath the ice of Antarctica today, heated by the Earth's internal warmth. Similar systems would have existed during Snowball Earth events. These hidden rivers and lakes, flowing in darkness beneath kilometers of ice, created their own unique ecosystems. Completely isolated from the frozen surface world above the atmosphere during Snowball Earth periods, was very different from the air we breathe today. With most of the planet's surface covered in ice, there was very little evaporation from oceans and lakes. making the air extremely dry. The reduced atmospheric moisture meant that precipitation was much less frequent than it would be in warmer periods. Though when snow did fall, it could accumulate rapidly in the frigid conditions. The low levels of carbon dioxide, which had contributed to the initial cooling, meant that the greenhouse effect was minimal, allowing heat to escape from the planet much more efficiently than it can today. Wind patterns during these frozen periods were unlike anything we experience in our current climate. The massive ice sheets created their own weather systems, with cold, dense air flowing off the ice like invisible waterfalls, creating fierce winds that could sandblast exposed rock surfaces with particles of ice and snow. These katabatic winds, as scientists call them, could reach incredible speeds as they accelerated down the slopes of the ice sheets, creating conditions that would have been lethal to any complex life forms. Yet even in these harsh conditions, the planet maintained its beauty and complexity. The interaction of sunlight with the ice and snow created optical phenomena that would have been breathtaking to behold. Sundogs, halos, and other atmospheric effects would have painted the sky with circles and arcs of light, while the aurora, fed by the same solar particles that create northern lights today, would have danced across the polar skies in brilliant displays of green and blue fire. In the midst of this frozen world, where silence reigned and ice stretched from horizon to horizon, life faced its greatest challenge. Yet life, as we've learned time and again throughout Earth's history, possesses an almost miraculous ability to persist, to find ways to survive and even thrive in conditions that seem impossible. The Snowball Earth periods were no exception to this remarkable resilience. Though the forms of life that endured these frozen millennia were very different from the complex organisms we're familiar with today, during these ancient times, life on Earth was still in its relative infancy. The complex plants and animals that would eventually populate our world were still hundreds of millions of years in the future. Instead, life consisted primarily of microscopic organisms, bacteria, archaea, and the first simple eukaryotic cells that would eventually give rise to all complex life forms. These tiny beings might seem insignificant to our eyes, but they were the pioneers that would eventually inherit the Earth and give rise to the incredible diversity of life we see today. Any of these ancient microorganisms possessed abilities that seem almost magical to us today. Some could survive being completely frozen for extended periods, entering a state of suspended animation where all biological processes slowed to nearly zero. When conditions improved and liquid water became available again, these hardy survivors could resume their normal activities as if awakening from a long sleep. It's a capability that some organisms retain today. We can find bacteria in the permafrost of the Arctic that have been frozen for thousands of years, yet still retain the ability to spring back to life when thawed. The volcanic oases we discussed earlier would have been crucial refuges for life during the Snowball Earth periods. Around these geothermal features, small communities of organisms could persist in the warm, liquid water that remained unfrozen despite the global ice coverage. These environments, with their steady heat sources and unique chemistry, became like laboratories where life could continue to evolve and diversify, even while the rest of the planet remained locked in ice. Some scientists believe that these volcanic refuges may have been where some of life's most important innovations first developed. The extreme conditions around hot springs and volcanic vents create unique challenges that require creative biological solutions. Organisms living in these environments must cope with high temperatures, unusual water chemistry, and limited resources conditions that favor the evolution of highly efficient and adaptable biological systems. But life during Snowball Earth periods wasn't confined only to these warm oases. Recent research has revealed that even in the ice itself, microscopic communities of organisms could survive and grow, just as we find bacteria living in the ice of glaciers today. Ancient microorganisms likely found ways to make homes within the crystal structure of the planetary ice sheets. These ice-dwelling communities would have existed in an environment unlike anywhere else on Earth, a world of perpetual cold and limited nutrients, where survival required extraordinary adaptations. The ocean beneath the ice also harbored life, though in forms and communities very different from what we might expect. Even when the surface of the ocean was completely frozen, liquid water remained below, especially in the deeper regions where pressure and residual heat from the Earth's interior prevented complete freezing. These hidden seas became refuges where marine life could persist throughout the frozen periods. The chemistry of these ice-covered oceans was unique and fascinating. Without contact with the atmosphere above, the water couldn't exchange gases in the normal way. Oxygen levels likely dropped significantly, creating conditions that favored organisms capable of living without this crucial gas. Meanwhile, nutrients that normally would be cycled between the ocean and atmosphere remained trapped in the water, creating a different kind of aquatic environment than had existed before or would exist again. Some of the most intriguing evidence for life during Snowball Earth periods comes from chemical signatures preserved in rocks from this time. These ancient stones contain patterns of carbon isotopes that tell us about the biological processes that were occurring when the rocks were formed. The ratios of different carbon isotopes can reveal whether organisms were photosynthesizing, breaking down organic compounds, or engaging in other biological activities. What these chemical clues tell us is that life didn't just survive the Snowball Earth periods. It remained active and continued to evolve. The organisms that lived through these frozen times developed remarkable strategies for survival that we're only beginning to understand. Some likely produced natural antifreeze compounds that prevented ice crystals from forming within their cells. Much like the antifreeze proteins found in Arctic fish today, others may have developed the ability to remain active at much lower temperatures than their ancestors, allowing them to continue growing and reproducing even in near-freezing conditions. Perhaps most remarkably, some organisms may have learned to use the ice itself as a habitat. Ice isn't the uniform, sterile environment we might imagine. Within its crystal structure are tiny pockets of liquid water, channels where dissolved minerals create brine that remains liquid even at temperatures well below the normal freezing point of pure water. These microscopic liquid spaces within the ice could have served as nurseries where organisms could grow and multiply. Even while surrounded by solid ice on all sides, the ability of life to persist through the Snowball Earth periods had profound implications for the future evolution of our planet. The organisms that survived these harsh conditions were, in many ways, the winners of one of evolution's greatest tests. They had proven their ability to endure extreme conditions, to adapt to environments unlike anything that had existed before, and to maintain the complex chemical processes that define life, even when the planet itself seemed hostile to their existence. When the ice finally began to retreat, these hardy survivors found themselves inheriting a world that was very different from the one their ancestors had known. The massive ice sheets had ground down mountains, carved new valleys, and redistributed minerals and nutrients across the planet's surface. The oceans, when they finally thawed, had different chemistry than before the atmosphere itself had been altered by millions of years of limited gas exchange. Into this transformed world, the survivors of the Snowball Earth periods could expand and diversify, taking advantage of new opportunities and filling new ecological niches. This process of survival, adaptation, and subsequent diversification may have been one of the key drivers in the evolution of complex life on Earth. The challenges posed by the Snowball Earth periods may have selected for organisms with greater flexibility, more sophisticated cellular machinery, and improved ability to cope with environmental change. These traits would prove invaluable in the millions of years that followed. As life continued to evolve toward greater complexity and diversity, the legacy of life's persistence through the Snowball Earth periods extends far beyond the organisms that directly experience these events. The genetic innovations, the biochemical pathways, and the adaptive strategies that evolved during these harsh times became part of the toolkit that life would use to colonize every environment on Earth, from the deepest ocean trenches to the highest mountain peaks, from scalding hot springs to permanently frozen soils. Life today continues to draw upon the lessons learned during those ancient frozen millennia as we reflect on this remarkable chapter in life's story. We're reminded of the incredible resilience and creativity that characterizes living systems. Even in conditions that seem absolutely hostile to life, organisms find ways not just to survive, but to continue the long, slow process of evolution that would eventually lead to the rich and diverse biosphere. We know today the Snowball Earth periods weren't just interruptions in life's story. They were chapters that helped write the rules for everything that would follow. Imagine, if you will, trying to picture what life could possibly look like on a planet entirely encased in ice. When we think of our vibrant, green Earth today, teeming with forests and oceans and countless creatures, it seems almost impossible to believe that there was once a time when our world resembled something more like Jupiter's moon Europa than the warm, welcoming home we know today. Yet during those extraordinary Snowball Earth events, life didn't simply disappear. Instead, it found ways to persist, to adapt, and remarkably, to continue evolving in ways that would eventually lead to the magnificent diversity we see around us today. The story of life during these frozen epochs is one of incredible resilience and ingenuity. Think about the most extreme environments on Earth today where life still manages to thrive. We find bacteria living in boiling hot springs, organisms surviving in the deepest ocean trenches where no sunlight ever reaches, and hardy microbes making their homes in the most acidic pools imaginable. Life, it seems, has an almost magical ability to find a way to survive and even flourish in conditions that would seem absolutely impossible to us. During the Snowball Earth periods, this remarkable tenacity was put to perhaps its greatest test in our planet's history, when the Great Freeze began to take hold. Most life on Earth at that time was microscopic. These weren't the complex plants and animals we're familiar with today, but rather tiny, single-celled organisms that had been quietly going about their business in the oceans for billions of years. These microscopic pioneers included various types of bacteria and archaea, some of which had already developed remarkable survival strategies that would serve them well during the coming ice age. Some could survive without oxygen. Others had learned to extract energy from chemicals rather than sunlight. And many possessed the ability to enter dormant states when conditions became too harsh for active living. As the ice began to spread across the oceans, these tiny organisms faced challenges that would have seemed insurmountable. The surface waters, where many had lived for eons, became solid ice, sometimes kilometers thick. The sunlight that photosynthetic organisms depended upon was blocked almost entirely, creating a world of perpetual twilight beneath the frozen surface. Temperatures plummeted to levels that would kill most modern life forms instantly. Yet somehow, in the face of these seemingly impossible conditions, life found refuges where it could continue to exist. One of the most important of these refuges was found in the deep ocean. Far below the frozen surface, even during the most severe Snowball Earth events, the deepest parts of the ocean never froze completely solid. The immense pressure at these depths, combined with heat still radiating from Earth's interior and the geothermal activity at underwater volcanic vents, created pockets of liquid water that remained accessible to life. These deep-sea sanctuaries became like underwater ark ships, preserving precious cargo of living organisms through the long winter of our planet's youth. In these dark depths, communities of organisms continued to thrive around hydrothermal vents, those underwater geysers that spew superheated, mineral-rich water from deep within the earth. These remarkable ecosystems operate on entirely different principles than the sun-dependent life we're familiar with at the surface. Instead of photosynthesis, the foundation of life around these vents is chemosynthesis, a process where bacteria extract energy from chemicals like hydrogen sulfide and methane that pour out of the Earth's interior. These chemical-eating bacteria formed the base of food webs that supported other organisms, creating islands of life in an otherwise frozen world. But the deep ocean wasn't the only place where life managed to persist. Scientists have discovered evidence that some organisms found ways to survive even in the frozen surface waters. Trapped within the ice itself, microscopic pockets of liquid brine remained unfrozen due to their high salt content. These tiny liquid inclusions, sometimes no bigger than the width of a human hair, became microscopic oases where hardy bacteria and archaea could continue to live and reproduce. Albeit very slowly, it's a remarkable thought that even within the solid ice that covered our planet, there were countless tiny communities of organisms carrying on with the business of life. Some researchers believe that certain areas of the ocean surface may have remained ice-free even during the most severe phases of Snowball Earth. These hypothetical refugia, perhaps maintained by volcanic activity or unusual ocean currents, would have been like life preservers thrown to drowning passengers on a sinking ship. In these small pockets of open water, photosynthetic organisms could have continued to harness what little sunlight managed to penetrate the planet's altered atmosphere, maintaining populations that would later spread and repopulate the world. When the ice finally began to retreat, the most fascinating aspect of life during these frozen periods wasn't just survival, but continued evolution. The extreme conditions of Snowball Earth created powerful selective pressures that drove innovation in the microscopic world. Organisms that could better tolerate cold, that could survive with less energy, or that could find new ways to extract nutrients from their environment had significant advantages over their less adaptable relatives. This process of natural selection, working over millions of years of frozen conditions, helped shape the genetic toolkit that would later be used to build more complex forms of life. There's something almost poetic about the idea that some of life's most important evolutionary innovations may have occurred during Earth's darkest and coldest chapters, like a master craftsman working quietly in a secluded workshop. Life used the extreme conditions of Snowball Earth as an evolutionary laboratory, experimenting with new biological technologies that would prove crucial for the future. The very harshness of these frozen worlds created opportunities for innovation. that might never have emerged under more comfortable circumstances. One of the most significant developments during this time was the continued refinement of cellular cooperation before the Snowball Earth events. Most life consisted of simple, single-celled organisms that lived independently, but the extreme stress of the frozen world encouraged cells to work together in new ways. Some began forming colonies where individual cells specialized in different functions, with some focusing on gathering nutrients, while others concentrated on protection or reproduction. This cooperation laid important groundwork for the later evolution of truly multicellular organisms, where cells would become so integrated that they could no longer survive independently. The scarcity of resources during the Ice Ages also drove innovations in how organisms stored and used energy in a world where food was scarce and conditions were unpredictable. Any organism that could survive longer periods without nutrients, or that could extract more energy from limited resources, had a tremendous advantage. This selective pressure led to the development of more efficient metabolic pathways and better methods of energy storage. These innovations would later prove crucial when life began to diversify and become more complex. Most intriguingly, some scientists believe that the Snowball Earth periods may have played a crucial role in the development of sexual reproduction. The ability to combine genetic material from two different parents creates offspring with genetic combinations that neither parent possessed alone. This genetic shuffling becomes particularly valuable during times of environmental stress, as it increases the chances that at least some offspring will possess combinations of traits that help them survive new challenges. The extreme and changing conditions during and after Snowball Earth events would have made this genetic diversity especially valuable, potentially providing strong evolutionary pressure for the development of sexual reproduction. The frozen oceans also created unique opportunities for genetic exchange between different populations of organisms. Normally, populations of microbes living in different parts of the ocean might remain genetically isolated from each other for long periods, but the dynamic nature of ice formation and melting during Snowball Earth events constantly mixed and redistributed organisms, bringing together populations that might otherwise never have interacted. This mixing allowed beneficial genetic innovations that arose in one population to spread to others, accelerating the pace of evolutionary change across the entire biosphere. Some of the most remarkable evolutionary innovations during this time involved the development of new survival strategies that we still see in organisms today. The ability to enter dormant states, where an organism essentially pauses its biological processes and waits for better conditions, became refined during these harsh periods. We can see the legacy of these ancient innovations in modern organisms that can survive being completely dried out, frozen solid, or deprived of food for extended periods. These survival strategies, originally developed to weather the extreme conditions of Snowball Earth, continue to serve life well in challenging environments today. The development of antifreeze proteins represents another fascinating evolutionary innovation from this time. These remarkable molecules work like biological antifreeze, preventing ice crystals from forming inside cells, even at temperatures well below the normal freezing point of water. Modern organisms living in polar regions, from Arctic fish to Antarctic bacteria, still use versions of these ancient molecular tools. The fact that such similar antifreeze systems exist in organisms that are otherwise very different suggests that these proteins may have first evolved during the global ice ages of Earth's distant past. But Perhaps the most profound evolutionary development during the Snowball Earth periods was the continued refinement of photosynthesis itself, the organisms that could still photosynthesize. During these dark times faced enormous challenges with most sunlight blocked by ice and altered atmospheric conditions. They had to become incredibly efficient at capturing and using what little light was available. The selective pressure led to improvements in the molecular machinery of photosynthesis that would later prove crucial when conditions improved and these organisms began to diversify. The cyanobacteria, those remarkable organisms that had first learned to split water molecules and release oxygen as a waste product, continued to evolve during the frozen periods. Some developed the ability to adjust their photosynthetic apparatus depending on the available light conditions, making them incredibly versatile survivors. Others evolved new pigments that could capture different wavelengths of light, allowing them to make use of whatever illumination managed to penetrate the icy world. These innovations in light harvesting would later contribute to the explosion of photosynthetic diversity that followed the melting of the ice. As we delve deeper into the story of life during these frozen epochs, we encounter one of the most fascinating aspects of survival in such extreme conditions: the development of sophisticated chemical communication systems. In a world where finding other organisms became increasingly difficult, and where the normal patterns of life were completely disrupted, the ability to send and receive chemical signals became more important than ever before. Like lighthouses guiding ships through treacherous waters, these molecular messages helped organisms find each other, coordinate their activities, and work together to survive the long winter. Even today, bacteria and other microorganisms use complex chemical signaling systems to communicate with each other. They release specific molecules into their environment that carry information about food availability, population density, threats, and opportunities for cooperation. During the Snowball Earth periods, these communication systems likely became even more sophisticated and important. In a world where resources were scarce and conditions were constantly changing, the ability to quickly share information about survival strategies could mean the difference between thriving and extinction. One particularly intriguing aspect of chemical communication during these frozen times involves the role of biofilms. These are communities of microorganisms that stick together and create protective matrices around themselves, somewhat like microscopic cities with their own infrastructure and communication networks. During Snowball Earth events, biofilms may have provided crucial protection against the harsh conditions, while also serving as centers for chemical communication and resource sharing. Organisms within these biological communities could share nutrients, exchange genetic material, and coordinate their responses to environmental challenges. Chemistry of the frozen oceans themselves created unique opportunities and challenges for life. As seawater freezes, it doesn't form a uniform solid block of ice. Instead, it creates a complex structure filled with channels, pockets, and inclusions of concentrated brine. These briny spaces had very different chemical properties than normal seawater, with much higher concentrations of salts and other dissolved substances for organisms trapped in these environments. This meant adapting to chemical conditions unlike anything in the modern ocean. Some bacteria learned to thrive in these highly concentrated brine pockets, developing mechanisms to cope with salt levels that would be lethal to most modern organisms. These adaptations required significant changes to their cellular machinery, including modifications to their cell walls and the development of specialized proteins that could function in high-salt environments. The descendants of these salt-tolerant organisms, known as halophiles, still exist today and continue to amaze scientists with their ability to live in extremely salty conditions. Unique chemistry of the frozen oceans also affected the availability of essential nutrients that organisms needed to survive. Elements like nitrogen, phosphorus, and iron, which are crucial for building proteins and other biological molecules, became concentrated in unusual ways as the ice formed and reformed. Some organisms learned to take advantage of these concentrations, developing new biochemical pathways that could extract and use nutrients more efficiently from these altered environments. Perhaps most remarkably, the chemical conditions during Snowball Earth may have encouraged the development of entirely new types of metabolism. Some organisms began experimenting with using different chemicals as energy sources, leading to metabolic pathways that we still see in certain bacteria today. These alternative forms of metabolism, often involving the processing of sulfur compounds, metal ions, or organic molecules in ways that don't require oxygen or sunlight, provided crucial backup systems when traditional energy sources became unavailable. Development of these diverse metabolic strategies had profound implications for the future of life on Earth. When the ice finally began to melt and conditions started to improve, the biosphere had a much more varied toolkit of survival strategies than it had possessed before the freeze began. This metabolic diversity would prove crucial during the dramatic environmental changes that accompanied the end of each Snowball Earth event, and it laid the foundation for the incredible biochemical diversity we see in life today as we continue our gentle journey through this frozen chapter of Earth's history. We come to understand that survival during the Snowball Earth periods wasn't just about individual organisms developing better ways to cope with harsh conditions. It was also about the development of complex networks of interdependence and cooperation that allowed entire communities of organisms to persist through the long, dark winters. These biological networks, invisible to the naked eye but crucial for survival, created a web of mutual support that helped life weather its greatest challenge. Picture, if you will, a modern ecosystem like a forest or a coral reef. The health and survival of each species depends not just on its own abilities, but on its relationships with countless other organisms. Trees depend on fungi that help their roots absorb nutrients, while providing the fungi with sugars in return. Coral animals house algae that photosynthesize for them, while protecting the algae from predators. These relationships, called symbioses, create resilient communities where the whole becomes greater than the sum of its parts. During the Snowball Earth periods, similar but much simpler networks of cooperation developed among the microscopic inhabitants of the frozen world. One of the most important types of cooperation involved the sharing of essential nutrients in the nutrient-poor environment of the frozen oceans. Any organism that could produce vitamins, amino acids, or other essential compounds became incredibly valuable to its neighbors. Some bacteria specialized in producing these crucial substances, while others focused on different survival strategies like finding new energy sources or providing protection from environmental stresses. This division of labor allowed communities of different organisms to survive together in conditions where none could have survived alone. The concept of metabolic cooperation became particularly important during these times. Different types of organisms developed complementary metabolic pathways, where the waste products of one organism became the food source for another. These metabolic chains created closed loops where nothing was wasted, maximizing the efficiency of resource use in environments where every molecule was precious. Some of these ancient partnerships may have been the precursors to the complex, symbiotic relationships we see in modern organisms. Communication played a crucial role in maintaining these survival networks. Organisms developed increasingly sophisticated ways to signal their needs, advertise their services, and coordinate their activities. Chemical signals became more specific and complex, allowing for more nuanced forms of cooperation. Some bacteria learned to produce signals that could attract beneficial partners while repelling potential competitors or threats. Others developed the ability to detect distress signals from their partners and respond with appropriate help. The physical structure of the frozen environment also shaped how these biological networks developed. The channels and pockets within the ice created natural highways for chemical communication and organism movement. These icy corridors connected different communities and allowed for the exchange of organisms, genetic material, and chemical messages across vast distances. In some ways, the frozen ocean became like a vast three-dimensional city, with its own transportation networks and communication systems. Particularly fascinating aspect of these survival networks was their ability to respond collectively to environmental changes. When conditions in one area became too harsh, organisms could signal the problem to their partners, who might then shift their activities to provide additional support. This kind of coordinated response gave these ancient communities a flexibility and resilience that no individual organism could have achieved on its own. It was like having an early warning system and emergency response team all rolled into one biological network. The development of these cooperative networks during Snowball Earth had long-lasting effects on the evolution of life. The genes and biochemical pathways that allowed for cooperation and communication were preserved and passed down through generations. When conditions eventually improved and life began to diversify, these ancient tools for cooperation became the foundation for more complex forms of multicellular life and ecosystem organization. Some scientists believe that the intense selective pressure for cooperation during Snowball Earth periods may have been crucial in setting the stage for one of the most important transitions in the history of life, the evolution of eukaryotic cells. These are the more complex cells that make up all plants, animals, fungi, and many other organisms today. Eukaryotic cells are thought to have originated when different types of bacteria began living together so closely that they essentially became a single organism. This kind of extreme cooperation may have been more likely to evolve during the harsh conditions of Snowball Earth, when the benefits of working together were literally a matter of life and death. Legacy of these ancient survival networks continues to influence life on Earth today. Many of the most important relationships in modern ecosystems, from the bacteria in our guts that help us digest food to the fungi that help plants absorb nutrients from soil, trace their origins back to these early experiments in cooperation. The frozen worlds of Earth's distant past taught life some of its most important lessons about the value of working together, lessons that continue to shape the living world around us. As we reflect on these remarkable survival networks, we begin to see that the Snowball Earth periods, despite their harshness, were times of incredible innovation and creativity in the living world, far from being simply periods of endurance and suffering. They were times when life experimented with new forms of cooperation and communication that would prove crucial for its future success. The frozen Earth became a laboratory for testing the power of unity and mutual support, experiments whose results we can still see in every ecosystem on our planet today. Deep beneath the frozen surface of our Snowball Earth, something magnificent was stirring. while the world above lay locked in an icy embrace that had lasted for millions upon millions of years. The heart of our planet continued to beat with a steady, persistent rhythm. This rhythm would eventually become the salvation of all life on Earth, though it would take time for its effects to reach the surface. Imagine, if you will, sitting by a campfire on a cold winter's night. The flames dance and flicker, sending warmth out into the darkness, melting the frost that has gathered on nearby stones. Now picture that campfire magnified beyond all imagination, burning not with wood and kindling, but with the very rock and metal of Earth's core. This is the volcanic activity that began to stir beneath our frozen world, a gentle giant awakening from its slumber. The volcanoes of Snowball Earth were not like the dramatic eruptions we might see in movies today. They were more like gentle, persistent breaths of warmth rising from the deep places of our planet. Each breath carried with it something precious: carbon dioxide, that invisible gas that would prove to be the key to unlocking our frozen world. Day after day, year after year, century after century, these underground furnaces continued their patient work, slowly but steadily adding their contribution to the thin atmosphere above the ice. You see, during the height of the freeze, most of the processes that normally remove carbon dioxide from the atmosphere had ground to a halt. The oceans were locked away beneath miles of ice, unable to absorb the gas as they normally would. The chemical weathering of rocks, which typically consumes carbon dioxide over geological time, had slowed to barely a whisper because most rock surfaces were buried under the great ice sheets. It was as if Earth had held its breath. And now the volcanic exhalations were the only source of new air entering the system. This carbon dioxide began to accumulate in the atmosphere like coins collecting in a jar. At first, the change was imperceptible. The concentrations were still relatively low, and the ice reflected so much sunlight back to space that the additional warming effect was negligible. But volcanoes are nothing if not patient. And they continued their steady work. The gas continued to build, molecule by molecule, breath by breath, until something remarkable began to happen. The first signs of change were subtle, like the first hints of spring after a long winter in some places, particularly near volcanic regions where the Earth's warmth was strongest. Tiny patches of ice began to thin. These weren't dramatic melting events, but rather gentle thinning that might have taken thousands of years to become noticeable. The ice, which had been miles thick in many places, began to show its first signs of weakness as these small patches of ice thinned. Something wonderful happened. The dark rock and soil beneath began to peek through, like shy faces appearing at windows. These dark surfaces had a very different relationship with sunlight than the brilliant white ice that had covered them for so long, where ice reflected nearly all the sun's energy back to space, keeping the planet cold. These dark patches absorbed the warmth and held onto it, like a black sweater on a sunny day. This created what scientists call a positive feedback loop, though in this case, it was beautifully positive for life on Earth. The more ice that melted, the more dark surface was exposed. The more dark surface that was exposed, the more heat was absorbed. The more heat that was absorbed, the warmer the planet became. And the warmer the planet became, the more ice melted. It was like a gentle spiral of warming that began slowly but gradually gained momentum at the same time. The continuing volcanic activity was pushing carbon dioxide levels higher and higher. Scientists estimate that during the end stages of Snowball Earth, the atmosphere may have contained levels of carbon dioxide hundreds of times higher than what we see today. This created an incredibly powerful greenhouse effect. wrapping our planet in an invisible blanket of warmth that began to work its magic on the ancient ice. The thawing process that followed was unlike anything our planet had experienced before or since. Imagine trying to melt an ice cube that's the size of a mountain. Then imagine doing that to ice sheets that covered entire continents. The scale was staggering, and the process took time that stretches our ability to comprehend. We're talking about changes that unfolded over hundreds of thousands, perhaps millions of years. But when the thawing began in earnest, it was spectacular. The ice didn't just disappear gradually. In many places it retreated in dramatic fashion. Enormous ice cliffs, some perhaps thousands of feet high, began to calve and collapse into the slowly warming oceans below. The sound must have been incredible. Imagine the deep groaning and cracking of ice sheets larger than continents, echoing across a world that had been silent for millions of years. As the ice retreated, it revealed a world that had been hidden for eons. The landscape beneath was scarred and carved by the massive weight of the ice, polished smooth in some places, and gouged deeply in others. Rivers that had been frozen solid for millions of years began to flow again, carrying the meltwater in torrents toward the growing oceans. The sound of running water returned to a world that had forgotten what it sounded like. What emerged from the Great Thaw was a world almost unrecognizable from the one that had entered the deep freeze. The extreme greenhouse conditions that had been necessary to melt the global ice sheets didn't simply disappear once the job was done, like a pendulum swinging from one extreme to another. Earth went from being a frozen snowball to what scientists call a hothouse world, a planet where temperatures soared far above anything we experience today. Picture the most swelteringly hot summer day you can remember, but imagine that warmth extending from the equator all the way to the poles. There were no ice caps anywhere on Earth, no glaciers clinging to mountain peaks, no frozen tundra stretching across the high latitudes. Even the Arctic regions, which we think of as permanently cold today, basked in temperatures that might remind you of a warm spring day in more temperate climates. The oceans, released from their icy prison, began to circulate freely for the first time in millions of years. But these weren't the cool, blue oceans we know today. The extreme greenhouse conditions heated the water to temperatures that seem almost unimaginable. Surface waters in many regions may have reached temperatures of 50 to 60 degrees Celsius, hot enough to make a relaxing bath, but spread across entire ocean basins. This hothouse world was painted in colors and filled with phenomena that would seem alien to us today. The sky, loaded with carbon dioxide and water vapor, may have taken on hues of deep amber or copper, filtered through an atmosphere much thicker and more humid than our current storms. When they formed, would have been intense beyond our modern experience, with so much heat and moisture in the atmosphere. The weather systems that developed had access to enormous amounts of energy. The chemistry of the oceans during this time was particularly fascinating. The extreme heat meant that many minerals that normally remain dissolved stayed in solution, creating waters that were rich in nutrients, but also quite different in their chemical composition from modern seawater. The combination of high temperatures and unusual chemistry created conditions that were both challenging and, in some ways, conducive to life. One of the most remarkable features of this hothouse world was how evenly distributed the heat was across the planet. Today, we have dramatic temperature differences between the equator and the poles, creating the diverse climate zones that support different types of ecosystems. But in the post-snowball hothouse, the temperature gradient from equator to pole was much gentler. A creature living near what we would consider the North Pole might experience conditions similar to what another creature experienced near the equator. This thermal equilibrium was maintained by ocean currents that were far more vigorous than those we see today. The extreme heat differential between the ocean surface and the cooler depths drove circulation patterns that mixed and redistributed heat with remarkable efficiency. It was as if the entire planet had become a giant heating system, with the oceans acting as the circulation fans that kept temperatures relatively even everywhere. Atmospheric pressure during this time was also significantly higher than what we experience today. Due to the enormous concentrations of carbon dioxide and water vapor, walking outside might have felt a bit like being at the bottom of a deeper atmosphere. With air that was noticeably thicker and more substantial, breathing would have been possible for modern humans, but the air would have tasted different, felt different, and carried with it the constant humidity of a world where evaporation was happening on a massive scale. Rivers during this period were unlike anything we see in our modern world, fed by constant evaporation and precipitation cycles. They carried enormous volumes of water, but more importantly, they carried with them the chemical products of weathering that was happening at an accelerated pace in the hot, humid conditions. The intense heat caused rocks to break down much more quickly than normal, releasing minerals and nutrients into the water systems that would eventually make their way to the oceans. This accelerated weathering process was actually Earth's way of beginning to regulate its own temperature, as the hot, humid conditions caused rocks to weather more rapidly. They consumed carbon dioxide from the atmosphere in the chemical reactions involved in breaking down the minerals. It was a slow process, taking millions of years, but gradually the planet began to pull some of that excess carbon dioxide out of the air and lock it away in chemical compounds. The landscape itself was transformed. By these conditions, in the absence of ice and with abundant heat and moisture, erosion and sedimentation processes operated at rates far exceeding what we see today. Mountain ranges that had been carved and polished by the great ice sheets now faced a different kind of sculpting from the intense chemical weathering and the powerful river systems that developed in the hothouse conditions into this dramatically transformed world. Life began to venture forth with a tentative curiosity that would soon blossom into an explosion of creativity and diversity. Unlike anything our planet had seen before, the organisms that had survived the Great Freeze in their hidden refuges now found themselves inheriting a world of unprecedented opportunity. It was as if they had been handed the keys to an entire planet and told they could redesign it. However, they wished the first pioneers to emerge were, naturally, the microscopic organisms that had always been life's most intrepid explorers: bacteria and archaea, those ancient forms of life that had learned to thrive in every conceivable environment, quickly began to colonize the newly available habitats. But these weren't just any bacteria. They were the descendants of survivors, organisms whose lineages had proven they could endure the most extreme conditions imaginable. The warm, nutrient-rich oceans of the hothouse world were like a vast cafeteria that had been closed for millions of years and was suddenly reopened with a completely restocked menu. The accelerated weathering of rocks had released enormous quantities of minerals and nutrients into the water systems, creating conditions that were incredibly favorable for life. Phosphorus, nitrogen, iron, and countless other elements that life needs to build itself were available in abundance. But perhaps more importantly, the chemical conditions in these post-snowball oceans were perfect for fostering innovation in the way life processes energy and materials. The unusual chemistry, combined with the extreme temperatures and the novel environmental conditions, created selection pressures that encouraged experimentation with new ways of living. It was as if life had been given a completely new laboratory to work in, with tools and materials it had never had access to before. One of the most significant developments during this period was the refinement and expansion of photosynthesis. The organisms that could harness sunlight had obvious advantages in this bright, warm world, but they also faced new challenges. The intense greenhouse conditions meant that the quality and quantity of light reaching the Earth's surface was different from what photosynthetic organisms had experienced before the freeze. This drove innovations in the molecular machinery of photosynthesis, leading to more efficient and sophisticated ways of capturing and using solar energy. The cyanobacteria, those remarkable organisms that had been among the first to develop oxygen-producing photosynthesis, found themselves particularly well-suited to the post-snowball world. They began to proliferate in ways that would have been impossible during the frozen period, forming massive blooms and colonies in the warm, shallow seas. Their success had profound implications for the entire planet, as they began to pump oxygen into the atmosphere at rates that dwarfed their previous contributions. This oxygen production was crucial because it began the process of moderating the extreme greenhouse conditions. Oxygen is a reactive gas, and as its concentrations increased, it began to participate in atmospheric chemistry that helped to gradually reduce the overwhelming levels of carbon dioxide. It was a slow process, taking place over millions of years, but it represented the beginning of Earth's return to more moderate conditions. Meanwhile, other forms of life were experimenting with entirely new ways of existing. The extreme conditions of the hothouse world had created chemical gradients and energy sources that hadn't been available before. Some organisms learned to exploit these new opportunities, developing metabolisms that could thrive on the unusual chemistry of the post-snowball environment. These innovations would prove valuable not just for survival in the immediate aftermath of the thaw, but would become part of life's permanent toolkit for dealing with challenging conditions. The abundance of nutrients and energy in the hothouse world also allowed for experiments in size and complexity that hadn't been possible during the resource-scarce conditions of the frozen period. Organisms could afford to invest energy in building more elaborate structures, developing more sophisticated cellular machinery, and experimenting with new ways of interacting with their environment. It was during this period that many of the fundamental innovations in cellular biology may have been perfected. One of the most fascinating aspects of life's response to the post-snowball world was how quickly adaptation occurred within what seems like a remarkably short time in geological terms. Perhaps only a few million years, life had not only recolonized the available habitats but had begun to fundamentally alter them. The activities of these pioneering organisms began to change the chemistry of the oceans, the composition of the atmosphere, and even the physical structure of the seafloor. Through their biological processes, the formation of what scientists call biofilms became particularly important during this period. These are communities of microorganisms that work together, sharing resources and creating protective environments for themselves. In the extreme conditions of the hothouse world, cooperation offered significant advantages over going it alone. These early experiments in biological cooperation may have laid the groundwork for the more complex multicellular life that would eventually follow as these microbial communities became more sophisticated. They began to create their own local environments within the larger hothouse world. They could modify the chemistry of their immediate surroundings, create protective barriers against harmful conditions, and even influence the flow of nutrients and energy in their vicinity. In essence, they were learning to be ecosystem engineers, shaping their world rather than simply responding to it. As millions of years passed in this hothouse world, something truly remarkable began to happen. The success of simple, single-celled life had created conditions that would make possible the next great leap in the story of life on Earth. The stage was being set for the emergence of complex, multicellular organisms, though this transition would happen slowly, almost imperceptibly at first. Like the first pale light of dawn gradually brightening an eastern horizon, abundant oxygen being produced by the flourishing cyanobacteria was beginning to fundamentally alter the chemistry of life itself. Oxygen, which had once been a toxic waste product that early life had to avoid or tolerate, was becoming a powerful tool that could be harnessed for more efficient energy production. Organisms that learned to use oxygen in their metabolism could extract far more energy from their food than those that relied on older, oxygen-free processes. This development was like discovering a new kind of fuel that was not only more powerful than anything used before, but was also becoming freely available in the environment. The organisms that mastered this new oxygen-based metabolism found themselves with energy budgets that their ancestors could never have imagined. They could afford to do things that had been impossible before, like building larger, more complex cells or maintaining more sophisticated internal structures. Increasing availability of oxygen also made possible the development of new kinds of cellular machinery. Complex molecules that require oxygen to function properly could now be incorporated into the basic toolkit of life. This opened up entirely new possibilities for how cells could operate, how they could interact with their environment, and how they could work together with other cells. One of the most significant innovations that became possible during this period was the development of what scientists call eukaryotic cells, cells that contain specialized internal compartments, including a nucleus that houses the cell's genetic material. These were far more sophisticated than the simple, prokaryotic cells that had dominated life up to this point. Think of the difference between a one-room cabin and a modern house with specialized rooms for different activities. The eukaryotic cell was like upgrading from the cabin to the house. These complex cells didn't appear overnight. Of course, their development was a gradual process that may have taken hundreds of millions of years, but the hothouse conditions following Snowball Earth provided the perfect environment for this evolutionary experimentation. The abundant energy, the rich chemical environment, and the relative stability of the warm world all contributed to making these innovations not just possible, but advantageous. As these more complex cells became established, they began to experiment with something that would prove to be one of the most important innovations in the history of life: cooperation between different cells. Instead of each cell living independently, some began to work together, forming colonies where different cells could specialize in different tasks. It was the beginning of true multicellular life. First multicellular organisms were probably quite simple, perhaps just clusters of identical cells that could coordinate their activities in basic ways. But even this simple cooperation offered significant advantages. A group of cells working together could be larger than any individual cell, making them harder for predators to consume. They could also divide up the work of survival, with some cells specializing in gathering food, others in reproduction, and still others in protection. The warm, stable conditions of the hothouse world were perfect for these early experiments in multicellularity. The organisms didn't have to deal with dramatic temperature changes, ice ages, or other environmental stresses that might have disrupted the delicate coordination required for multicellular life to work. They had the luxury of time and stability to work out the complex biochemical and genetic mechanisms needed to make multicellular organisms successful. As these early multicellular organisms became more sophisticated, they began to develop features that we would recognize as the precursors to the complex life forms that would eventually populate our planet. Some developed primitive sensing systems that allowed them to detect and respond to their environment. Others experimented with different shapes and structures that could help them move through the water or anchor themselves in favorable locations. Diversity of forms that emerged during this period was staggering. The fossil record from the time following Snowball Earth events shows an explosion of different body plans and life strategies. It was as if life had been given a blank canvas and had decided to try every possible way of existing. Some organisms became filter feeders, straining nutrients from the water. Others became predators, actively hunting their prey. Still others became photosynthetic, building their own food from sunlight and simple chemicals. This period of innovation wasn't just about biological forms, though the activities of these increasingly complex organisms began to have profound effects on their environment. They influenced ocean chemistry through their metabolic processes, created new kinds of sediments through their life activities, and began to establish the kinds of ecological relationships that would become the foundation for all future ecosystems. The development of predation, in particular, had revolutionary implications. For the first time in Earth's history, organisms were actively hunting and consuming other organisms. This created entirely new selection pressures that drove the evolution of defensive strategies, escape mechanisms, and protective structures. The arms race between predators and prey had begun, and it would prove to be one of the most powerful forces driving the evolution of complexity and diversity as the hothouse conditions gradually began to moderate due to the ongoing processes that were removing carbon dioxide from the atmosphere. Life found itself increasingly well-equipped to handle environmental change. The innovations that had been developed during the stable, warm period, complex cells, multicellular cooperation, diverse metabolisms, and sophisticated ecological relationships, provided a toolkit that would prove invaluable as Earth entered its next phase of environmental change. The stage was now set for one of the most dramatic chapters in the history of life on Earth. The simple, single-celled organisms that had survived the Great Freeze had not only recovered, but had used the opportunity provided by the post-Snowball world to reinvent themselves completely. They had developed the biological innovations that would make possible all the complex life that would follow, including, eventually, creatures complex enough to look back through deep time and piece together this remarkable story of survival, recovery, and transformation. The hothouse world was beginning to cool. The extreme greenhouse conditions were slowly moderating, and Earth was approaching a new era of relative stability. But the life that would inherit this more moderate world was fundamentally different from the life that had entered the Great Freeze millions of years earlier. It was more complex, more diverse, and more capable than ever before. The seeds of all future evolution had been planted, and they were ready to grow into forms that would have been unimaginable to the simple organisms that had first survived. Earth's frozen childhood. As we stand at the edge of our own climate story, the ancient whispers of Snowball Earth reach across billions of years to touch our modern world. Think of it as listening to the faint but persistent echo of a song that has traveled through the deepest caverns of time, each note carrying wisdom about how our planet responds to dramatic change today. As you walk through your daily life, you might not realize that you are surrounded by the descendants of the survivors, every tree that rustles in the wind outside. Your window, every bird that sings at dawn, every flower that blooms in your garden carries within its DNA the memory of those frozen eons. They are living libraries, their genetic code inscribed with the story of how life learned to endure the unendurable. The ice cores that scientists extract from Antarctica and Greenland are like frozen diaries, each layer a page written in the language of ancient atmospheres. When researchers examine these crystalline records, they find traces of those distant winters that lasted millions of years, the composition of the ice, the tiny bubbles of ancient air trapped within, all tell the same remarkable story that we have been exploring together. Perhaps the most humbling realization is how these ancient events illuminate our current moment. The carbon dioxide that accumulated in the atmosphere during Snowball Earth eventually reached concentrations that triggered the Great Thaw today. We find ourselves in a situation where carbon dioxide levels are rising at a pace that would have seemed impossible to the ancient Earth, yet the story of Snowball Earth reminds us that our planet has experienced dramatic climate shifts before, and life has found ways to adapt and thrive. Consider the delicate balance that keeps our modern world from sliding into either extreme. We live in what scientists call the Goldilocks zone of climate. Not too hot, not too cold, but just right. For the complex web of life we know today, the story of when Earth first froze solid teaches us how precious and fragile this balance truly is. It shows us that our planet's climate system has tipping points, moments where small changes can cascade into transformations that reshape the entire world. Modern climate scientists study Snowball Earth events not as curiosities from a distant past, but as laboratories for understanding how climate systems can shift dramatically. The mathematical models they use to predict future climate change are tested against these ancient events. Can their equations successfully recreate the conditions that led to global freezing? Can they accurately simulate the mechanisms that eventually broke the ice's grip on our planet? Each successful simulation strengthens our confidence in the tools we use to understand our current climate trajectory. Parallels are both comforting and sobering. Comforting because they show us that Earth has weathered extreme changes before and emerged not just intact, but enriched with new forms of life and greater complexity. Sobering because they remind us that the climate system can change in ways that completely alter the rules of existence for every living thing on the planet. There's something deeply beautiful about the way our planet has learned to heal itself over geological time, like a master artist who can turn a catastrophic spill of paint into an unexpected masterpiece. Earth has consistently transformed crisis into opportunity, devastation into innovation. The story of when Earth first froze solid is ultimately a story about resilience, but not the kind of resilience we usually think about. It's not the resilience of a single organism surviving harsh conditions, though that certainly happened. It's the resilience of an entire planetary system. The way oceans, atmosphere, continents, and life itself can work together to find new equilibriums, new ways of being that allow the grand experiment of existence to continue. When we look at the fossil record from the periods immediately following Snowball Earth events, we see what paleontologists call evolutionary radiations. These are moments when life explodes into new forms with remarkable creativity and speed. It's as if the extreme pressure of the frozen world compressed all of life's potential energy. And when the ice finally released its grip, that energy burst forth in a spectacular display of biological innovation. This Pattern teaches us something profound about how complex systems respond to stress. Sometimes the very conditions that seem most threatening to a system's survival can become the catalyst for its most significant advances. The organisms that survived the frozen world were not just lucky. They were fundamentally different from their ancestors. They had developed new molecular machinery, new ways of processing energy, new strategies for cooperation and competition. Modern biologists studying extremophiles, organisms that thrive in conditions previously thought to be impossible for life, often trace their remarkable abilities back to these ancient trials by ice, the bacteria that can survive in the boiling water of volcanic springs, the organisms that flourish in the crushing depths of ocean trenches, the microbes that can endure the vacuum of space itself, all carry genetic innovations that may have first emerged during the long frozen nights of Snowball Earth. But resilience, we learn from this ancient story, is not just about individual survival. It's about maintaining the connections and relationships that make complex systems possible during the frozen periods. The most successful organisms were often those that formed partnerships, that learned to share resources and work together in ways that their ancestors never had to attempt. This collaborative approach to survival became deeply embedded in the fabric of life on Earth today. When you eat a piece of fruit, you are participating in a partnership between plants and animals that may have been forged during those frozen epochs. When you see a forest thriving because of the intricate network of fungal connections between tree roots, you are witnessing a form of cooperation that learned its value during times when cooperation meant the difference between extinction and survival. Oceans themselves learned new forms of resilience during these events. The circulation patterns that had been disrupted by ice cover had to reorganize themselves as the world thawed. New currents formed, carrying nutrients and heat around the globe in patterns that had never existed before. These new oceanic highways became the foundation for marine ecosystems that would eventually give rise to the extraordinary diversity of sea life we know today. Even the solid Earth participated in this planetary resilience. The weight of massive ice sheets pressed down on continents, and when the ice melted, the land slowly rebounded, rising like a patient taking a deep breath after holding it for far too long. This geological breathing created new landscapes, new river valleys, new coastal configurations that provided fresh opportunities for life to explore and inhabit. Every mountain range tells a story, and many of those stories include chapters about when Earth first froze solid. If you know how to read the language written in rock layers, you can see the evidence everywhere. The peculiar formations called cap carbonates that sit like white caps on ancient rock sequences mark the moments when the Great Thaw began. These limestone layers formed as the ice-locked oceans suddenly came alive again, their chemistry changing so rapidly that minerals precipitated out of solution like snow falling upward from the seafloor. These geological signatures have become some of our most important teachers about how planetary systems can shift between dramatically different states. They show us that change, when it comes to climate systems, is not always gradual. Sometimes it can be sudden, tipping from one stable configuration to another in geological moments that span thousands rather than millions of years. The rocks also tell us about the incredible power of feedback loops in climate systems during Snowball Earth. The bright white ice reflected so much sunlight back to space that it became self-reinforcing. The colder it got, the more ice formed. The more sunlight was reflected away. The more sunlight was reflected away, the colder it got. It was a runaway process that might have continued indefinitely if not for the patient accumulation of volcanic carbon dioxide in the atmosphere. But the story written in stone also reveals the power of opposing feedback loops. Once the ice began to melt, the process reversed itself with equal determination. Dark ocean water absorbed heat that white ice had reflected. Warmer temperatures released more greenhouse gases from thawing permafrost and warming oceans. The warming accelerated until the planet swung to the opposite extreme, creating hothouse conditions that were as dramatic in their own way as the frozen world that preceded them. These lessons from deep time offer us a unique perspective on our current moment. Climate scientists studying current global warming often refer to the concept of tipping points, moments when gradual changes can trigger rapid shifts to entirely new climate states. The story of when Earth first froze solid provides us with detailed case studies of how such tipping points work on a planetary scale. But perhaps the most important lesson written in these ancient rocks is about the relationship between life and climate. We often think of climate as something that happens to life, as an external force that life must adapt to or perish. The Snowball Earth events reveal a more complex and hopeful reality. Life doesn't just respond to climate. Life participates in creating climate. The oxygen that made Snowball Earth possible was produced by living organisms. The carbon dioxide that eventually ended the frozen periods was processed and managed by biological systems. The very chemistry of the oceans and atmosphere that determines our planet's climate is an ongoing collaboration between geological and biological processes. This means that life is not just a passenger on the climate system. It's one of the drivers, and this gives us both responsibility and hope as we face our own climate challenges. We are not helpless observers of climate change. We are participants in the Earth system. And like the microorganisms that helped end the Snowball Earth events, we have the potential to influence the trajectory of our planet's climate story. If we could somehow listen to the entire 4.5 billion year history of our planet as a symphony, the Snowball Earth events would be among the most dramatic movements. They would be the passages where the music drops to a whisper, where individual instruments disappear one by one until only the most essential melodies remain, playing softly in the dark. But then, as we have discovered together, these quiet movements build toward crescendos of unprecedented power and beauty. When the ice finally released its grip and life exploded back into the warming world, it would be like every instrument in a vast orchestra suddenly joining in a celebration of existence itself. This musical metaphor helps us understand something important about the role of crisis in the story of life on Earth. The moments of greatest apparent catastrophe often become the launching points for life's most creative and expansive chapters. The extinction events that seem to threaten the very continuation of the story instead clear the stage for entirely new performances. New combinations of themes and variations that never could have emerged under the previous conditions. The organisms that inherited the post-Snowball Earth world were like musicians who had learned to play their instruments under the most challenging conditions imaginable. When normal conditions returned, they didn't just resume the old songs. They created entirely new forms of music. They experimented with harmonies and rhythms that their ancestors could never have imagined. And this brings us to one of the most remarkable aspects of the Snowball Earth story, how it reveals the creative power hidden within apparent destruction. The ice that covered the planet was not just an ending. It was also a beginning. It was the intermission between acts in the grand drama of terrestrial life. A pause that allowed the stage to be completely reset for the next phase of the performance. During those frozen millions of years, Evolution was not idle in the dark waters beneath the ice. In the thin films of liquid water that persisted in even the most unlikely places, life was experimenting with new possibilities. The extreme conditions served as a pressure chamber, compressing the potential for innovation until it was ready to burst forth with unprecedented vigor. Modern evolutionary biologists sometimes use the phrase evolutionary constraint to describe how established biological systems can become locked into particular patterns that limit their ability to explore new possibilities. The Snowball Earth events acted like a great liberation from such constraints. They swept away the established order so completely that life was free to reinvent itself from the molecular level up. This process of creative destruction and renewal is not unique to the ancient past. We can see it operating at many different scales and time frames throughout the history of life on Earth. Forest fires clear the way for new growth. Volcanic eruptions create fresh soil for pioneering plants, even in our own lives. We sometimes find that our greatest periods of growth and creativity follow times of challenge and upheaval. Symphony of Deep Time teaches us that change and continuity are not opposite forces. They are partners in the dance of existence, the most profound continuities. The themes that run through the entire 4 billion-year story of life on Earth are preserved and carried forward precisely through processes of transformation and renewal as we near the end of our journey through the story of when Earth first froze solid. It's natural to wonder what this ancient tale might tell us about the future, the Earth that will exist 1,000,000 years from now, or 10 million years from now, is being shaped by processes and decisions happening right now, just as the Earth we inhabit today was shaped by the events we have been exploring together. One of the most profound insights from Snowball Earth research is how it expands our sense of what is possible before scientists began to seriously consider the evidence for global glaciation. The idea that our entire planet could freeze solid seemed absurd. It violated our assumptions about how planetary systems work, about the limits of climate variability, about the conditions necessary for life to persist. But the evidence became overwhelming. The rocks told a story that couldn't be ignored, and scientists had to expand their understanding of how dynamic and surprising our planet's climate system could be. This expansion of scientific imagination has proven invaluable as we try to understand and predict the behavior of complex Earth systems. The mathematical models that climate scientists use today incorporate lessons learned from Snowball Earth events. They account for the kinds of feedback loops and tipping points that these ancient climate shifts revealed. They consider the possibility of rapid transitions between stable climate states, something that might not have been included in earlier modeling approaches. But perhaps more importantly, the story of when Earth first froze solid provides us with a longer perspective on the relationship between life and planetary change. It reminds us that life has survived and thrived through climate changes far more dramatic than anything in recorded human history. This doesn't minimize the challenges we face today, but it does provide a context for understanding the incredible resilience and adaptability that life has demonstrated over geological time. The microorganisms that survived beneath the ice during Snowball Earth events developed biochemical innovations that still influence the functioning of ecosystems today. The partnerships and cooperative strategies that proved essential during those difficult times became foundational to the complex web of relationships that supports modern biodiversity. The genetic diversity that was preserved through those bottlenecks became the raw material for the evolutionary radiations that followed. This suggests that the challenges our planet faces today while certainly serious and deserving of our urgent attention, are also opportunities for innovation and adaptation. The organisms living today, including ourselves, are the products of billions of years of evolutionary problem-solving we carry within our biological and cultural heritage, the accumulated wisdom of countless generations that have faced and overcome existential challenges. The story also suggests that the most effective responses to planetary-scale challenges often involve cooperation rather than competition. The organisms that thrived in the post-Snowball Earth world were those that had learned to form partnerships, to share resources, to create mutual support networks that were more resilient than any individual could be alone as we look toward our own future. These lessons from deep time offer both guidance and hope. They suggest that the path forward lies not in trying to prevent all change, which is neither possible nor desirable, but in learning to work with change in ways that preserve and enhance the conditions that make life possible. Every story needs an ending, but the story of when Earth first froze solid is not really ending at all. It's continuing right now. In the rocks that are forming on the ocean floor, in the ice that is accumulating in polar regions, in the atmospheric gases that are cycling between plants and animals, and the vast reservoirs of the sea. Same processes that drove the Snowball Earth events are still operating today. Though at different scales and intensities, volcanoes still release carbon dioxide into the atmosphere. Ocean currents still carry heat around the globe. Ice sheets still reflect sunlight back to space. Life still influences the chemistry of the atmosphere and oceans through countless biological processes. What has changed is the presence of a species, our own, that can study these processes, understand their implications, and make conscious choices about how to respond to them. We have become participants in the Earth system in ways that no previous species has ever been. We can read the story written in rocks and ice. We can model the behavior of climate systems. We can anticipate the consequences of different courses of action. This knowledge brings with it both power and responsibility. The microorganisms that helped end the Snowball Earth events did so unconsciously. Simply by following their biological programming, they couldn't anticipate the consequences of their actions or choose different strategies based on their understanding of planetary systems. We, on the other hand, can see the bigger picture. We can understand how our activities influence the Earth system. We can make choices based on our knowledge of how climate systems have behaved in the past and how they might behave in the future. We can work consciously to influence the trajectory of our planet's climate story. The story of when Earth first froze solid suggests that the most successful strategies for dealing with planetary scale challenges are those that work with natural processes rather than against them. The organisms that survived the frozen world were those that found ways to take advantage of the conditions they faced, rather than simply trying to resist them. Similarly, our most effective responses to current climate challenges are likely to be those that harness natural processes, that work with the Earth system rather than trying to overpower it. This might mean using the power of living systems to capture and store carbon dioxide, or designing our cities and agricultural systems to work with natural water cycles rather than against them. The story also suggests the importance of maintaining diversity and resilience in our responses to change. The ecosystems that recovered most successfully from Snowball Earth events were those that preserved the greatest variety of organisms and biological strategies. No single approach was sufficient to ensure survival through such extreme conditions. As we write the next chapter of our planet's climate story, we might take inspiration from this ancient wisdom Our responses to climate change are most likely to be successful if they are diverse, adaptive, and collaborative, if they draw on the full range of human creativity and knowledge, if they work with natural systems rather than against them, if they preserve and enhance the conditions that allow life to flourish in all its magnificent variety. The frozen world of Snowball Earth eventually gave way to a planet teeming with new forms of life, more diverse and resilient than anything that had existed before. The challenges we face today, while very real and requiring our urgent attention, also contain within them the potential for transformation and renewal. The story of when Earth first froze solid reminds us that crisis and opportunity are often two faces of the same coin, that the moments of greatest challenge can become the launching points for unprecedented innovation and growth. As we continue to study these ancient events, we continue to learn from them. New discoveries in geochemistry reveal details about the pace and extent of global freezing. Advances in molecular biology help us understand how organisms survived in extreme environments. Improvements in climate modeling allow us to test our theories about what triggered these events and what ended them. New piece of evidence adds another thread to the tapestry of understanding we have been weaving together, and each thread helps us see more clearly not just what happened in the distant past, but what might be possible in the future. The story of when Earth first froze solid is ultimately a story about possibility, about the incredible capacity for transformation and renewal that seems to be built into the very fabric of existence. Thank you for staying with me through this peaceful journey into when Earth first froze solid together. We've traveled through billions of years, witnessed the planet transform from a frozen ball of ice into a vibrant world teeming with life, and discovered how these ancient events continue to influence our understanding of climate, life, and planetary resilience. Today, I hope this story has given you a sense of wonder about the incredible journey our planet has taken, and perhaps a deeper appreciation for the remarkable resilience of life itself. The organisms that survived those frozen epochs are your ancestors, and mine, and the ancestors of every living thing on Earth today. Their story of perseverance and adaptation is written into our very DNA as you go about your daily life. I invite you to remember that you are part of this continuing story. Every breath you take participates in the ancient cycles that have been operating since long before the ice ever covered our world. Every choice you make about how to live on this planet becomes part of the next chapter in Earth's climate story. The story of when Earth first froze solid teaches us that our planet is far more dynamic, more resilient, and more surprising than we might have imagined. It shows us that life has an almost magical ability to find ways to persist and flourish even under the most challenging conditions, and it reminds us that we are not just observers of planetary processes, but active participants in shaping the future of this remarkable world we call home. If you enjoyed exploring this ancient chapter of Earth's history with me, I'd love for you to share this journey with others who might find wonder in these deep time stories. Consider subscribing if you'd like to join me for more gentle explorations of our planet's incredible past and the lessons it holds for our future. Until we meet again for another peaceful journey through the pages of Earth's history, take care, and remember that you are part of the most beautiful and resilient story ever told. The story of life on Earth. Sweet dreams, and thank you for being here.